I may have to pause at some point because I've got a dog wandering around this room and I don't want her to get into trouble. Over here, you lay down. I don't know if she'll listen to me or not. Okay, the first thing I want to do is look at some kind of a couple of qualitative situations and considering Lenz's law. And this is something that the direction of any magnetic induction effect is to oppose the cause of that effect. And this is going to take some thinking in quite a few cases, but let's go ahead and try to do these. And I tried to snip some problems out of the PDF version of the textbook that I happen to have, and they didn't work so well. Some of the illustrations just didn't show up in the PDF version. I guess I could have used the open source textbook and looked for problems, but let's see what this idea means in a few situations, and I'll kind of bring it back so we can, or keep that in mind. Anyway, one of the problems in the book, we have a circular loop of wire in a region of spatially uniform magnetic field. So that's what this loop of wire is, and the X's represent the magnetic field into the page in this case. Into the plane of determine the direction clockwise or counterclockwise of the induced current in the loop when B is increasing. So that means that we will have a magnetic field that's increasing into the page and increasing in strength. And keep Lenz's law in mind when we think about this thing. And it may help to think about the induced EMF equaling the negative of the flux of the magnetic field, the time derivative of the flux of the magnetic field. Anyway, so here's what happens because of Lenz's law. The magnetic flux through that coil of wire here into the page is increasing. Now, the direction of the magnetic induction effect is to oppose that increase in magnetic field, increase in magnetic flux through the coil here. Well, the way that it does that is that a current will be induced in the coil going in this direction. If the current goes in that direction, it'll produce a magnetic field going in this direction. That magnetic field will be caused by the current, and that will oppose the increase in the flux into the page caused by the increasing magnetic field. So if B is increasing, then the current will be counterclockwise. And I'm just going to abbreviate that as CCW, counterclockwise. Okay. The increase in magnetic flux into the page. Hang on. Gotta get the dog off the bed. That's not, you lay down over there. I hope I don't have to do that too many times. Anyway, that's what's going to happen. So if B is decreasing, so if B is decreasing, that means the amount of flux into the page through that coil in that direction is also going to be decreasing. The induced current will be in a direction to oppose that change. That means to try to maintain that. And if you have the current going in the clockwise direction, it'll produce a magnetic field into the page that tries to maintain or acts to maintain the same amount of flux going into the page. So in that case, if it's doing that, the current will be counterclockwise. And I'm just abbreviating that as CW there. And then C, if B is constant with the value B naught. Well, if there's no change in the magnetic field, that means no change in the amount of flux through that coil. There will be no induced current in that direction. It's only when you have a changing magnetic field that you get induced current. So that's something to keep in mind. There's a whole set of problems in the Lenz's law section, many of which are non-calculation problems, and you might try those things out and take a look at them. All right, let's try another one of these. This one, the current in figure E29.16, which is this one, obeys the equation I of t equals I naught e to the minus bt. Okay, where b is greater than 0. All right, so that's just a constant, but because it's got this e to the minus bt on it, that means there's an exponential decrease in the current. And so the current would, if you made a graph of it as a function of time, at time 0, it would have a value I naught, and then it's decreasing exponentially. So it'll be swooping down a curve like that. Find the direction, clockwise or counterclockwise, of the current that's induced in the round coil here for t greater than 0. Okay, well, it'll help to sketch the magnetic field that's produced by a current going in this direction. Use your right hand, point the thumb of your right hand in the direction of the current flow, and your fingers of your right hand can curl in the direction of the magnetic field. And it'll be, this is going to be a little hard to illustrate, but okay, a bunch of things like this. And oops, and I'm having them vanish when they go behind the wire, so you can tell what part's in front of the wire and what part's behind the wire. Well, what that means is that for this loop here, it's going to have magnetic field that's coming out of the page due to the current in that wire. So at any given time. And so there will be magnetic flux going in that direction through that loop. But the magnetic flux is decreasing, okay, because the current is decreasing, and that means the strength of the magnetic field will be decreasing. So with a flux out of the page that's decreasing, what would be an induced current direction that would maintain flux coming out of the page? Well, it would be a counterclockwise flux. And I say that not because I did a calculation to figure that out, but calculation to figure it out, but because if you have a counterclockwise current in that loop, it'll produce flux out of the page. And that's how you can oppose that decrease in the flux coming out of the page caused by the decreasing current up here. So another non-calculation type problem. And you just kind of reason your way through those things. Some of them are a bit challenging. There's one that I wanted to get. I don't know if I printed it off. I think I printed off everything but the illustration, which for some reason wasn't in the PDF version. And maybe it's because it was a pirated PDF of some sort. I don't know, but I'll have to look at what that illustration was. Anyway, this is 29.20. What's it look like? Now the dog was eating a paperclip. Okay, puppies. Okay, 29.20 is a relatively simple figure. It's got a circle of radius r. I guess I'll do it in green just for the heck of it. If I can. Oh, rats. Oh, well, it's going to be my, this circle may not look perfect when I'm done with it, but, oh, it's not too bad. Okay, got a circle of radius r, I think, and the magnetic field B, which is everywhere you see it on here, it's just dots. So that means it's a magnetic field that's coming out of the page. And this one actually has numbers, so we'll probably have to do some sort of a calculation for it. A circular loop of wire with a radius r of that much and resistance R equals 0.160 ohms is in a region of spatially uniform magnetic field as shown in figure 29.20, which is what this is. Magnetic field is directed out of the plane of the figure. Okay, we drew that. And it has an initial value of 8.00 Tesla and is decreasing at a rate of dB dt equals minus 0.680 Tesla per second. Is the induced current in the loop clockwise or counterclockwise? And then what is the rate at which electrical energy is being dissipated by the resistance of the loop? Okay, we don't know how to calculate this, and I'm not going to expect you to learn it, but we'll go ahead and I'll show you how to calculate it. So we'll have that. Okay, well, if the magnetic field is decreasing in strength, dB dt is negative, that means, and that's just the magnitude of the magnetic field, that means the magnetic flux through this loop is going to be decreasing in time. And so there will be an induced current that will oppose that decrease. Basically, it tries to maintain the status quo. And so the way that that can happen is if you have a current in the loop going in this direction, it will produce its own magnetic field out of the page and oppose that decrease in the magnetic field strength that's here. So let's see how that's going to work. And I guess we can put numbers on this thing. The induced EMF, which by the way will equal I times R. So we'll actually be able to calculate the current in this case, because we've got everything that we need, will equal, we know the direction of it, so I'm just going to say that it'll equal the time derivative of the flux of B dt. And we know it's going to be counterclockwise. I guess I could draw arrows on here, and that's our solution to part A. I may have to take this dog outside. I don't know. She's getting into mischief. Okay, well, what about the flux of B? What's that going to be? Well, that'll just be d by dt. Well, that's the derivative, but it'll equal the strength of the magnetic field times the area of this circle, which is just pi r squared. Now, the only thing that's changing in time is B, and so the I times R that we're interested in here is just going to be pi r squared dB dt, and they gave us dB dt. It's minus 0.680 Tesla per second. And the fact that it's got an initial value of 8 Tesla doesn't matter. Okay, all that matters is the rate at which it's changing. And so I can actually solve this for the current. This will be pi r squared over capital R. Capital R is resistance, not a radius. And I can multiply that by the dB dt. So let's go ahead and see what the numbers come out as. Pi times the radius is 0.0480 meters. And this will be an interesting application of units. Let's see, 0.160 ohms. And then dB dt, I guess we can put a minus sign on it, except we're after the magnitude of the current flow. We know which way it's going. So I'm going to ignore that here. Minus, or just call it 0.680 Tesla per second. Okay, now it may help to remember Ohm's law, which is that V is equal to I times R, which means R is going to be V over I. And I want to get more fundamental units for resistance. A volt is a joule per coulomb. So it'll be, that's an ohm. And ohm is going to equal a joule per coulomb divided by a coulomb per second. And when we divide by something by a fraction, we invert it and multiply. So this will end up being a joule second per coulomb squared is what we have there. Okay, so that's the ohms down there, and they're on the bottom of a fraction. And then I've got meters squared up there. I mean, it's no problem doing the calculation, but it's pretty hard to figure out what the units are going to be. So anyway, unit-wise, I'll have meters squared on top. I had ohms on the bottom, which happened to be that, but I'm going to invert that and multiply. So I'll have meters squared, coulombs squared per joule second. And then I've got a Tesla per second over there. So I'm going to have another 1 over seconds here. And let's see, that give me seconds squared down there. And then I've got a Tesla, which is a Newton per amp meter. Okay. Still kind of messy, but let's see what we can get here. Let's see, if I cross this out and cross that out, on top, I'll have a Newton meters. Okay, I think I'm going to have to pause this and go stick her outside in the pen, and you'll hear her barking from there. So, oh, you can't see. We'll slide that up. Okay, outside you go. May not be what you wanted, but that's what you're going to get. Come on, Pepper, this way. Oh, here. Okay, sorry about that. But I'm actually glad I took her out because she had to go. So anyway, I'm going to bring this meter over here and make that a Newton meter, which is a joule. So that divides that out. And now I'm going to take one of these coulombs and think coulomb per second. That's an amp on top. It divides with that amp. So I cross those out and I'll have 1 coulomb left. And that'll be a coulomb per second, which is an amp. So I will end up with a current here. And you really have to juggle these things to try to figure them out. So now we can just plug in the numbers. And, um, oh, it's asking the rate at which electrical energy is being dissipated by the resistance of the loop. And once I figure out the current, I'll show you an expression for that. But I'll just have pi times 0.0480 squared times 0.680 divided by 0.160. And I forgot to turn on my calculator. Try this again. Okay, and I would get a current, not a huge current, but 3 point, I guess I've got 3 sig figs everywhere. 0.8 times 10 to the minus 2 amps. So that's what I happen to have. Now, as far as calculating the power, there's a relation that power is equal to I times V, but in this case, V is equal to I times R. So I'd have I times R, which is just I squared R. Sometimes I guess we could think that since I times R is equal to that E, you'd get E is equal to IE. And we were doing this Friday afternoon, talking about different kinds of pi. So there you go. All kinds of cosmic connections here. Anyway, but I'll square that current and multiply it by the resistance. And we're not going to get a lot of power out of this thing, but that's all right. Um, and I get about 1.5 times, actually 1.51 times 10 to the minus fourth. And the units of power that you get out of here, this would be another challenging thing, but it'll end up being joules per second, which are watts. So we have that. And this is actually, you could recalculate that or recalibrate it. It's 151 microwatts. So not a whole lot of current here, but it's only one single loop of wire. And even though it's a pretty rapid change in the magnetic field, but the way you increase it is just wrap more loops around there, and then you can get a fair amount of current in those things. Okay, so there's a calculation one with Lenz's law. And I have some other problems here. I think this one is from an earlier section in the textbook, but it's one that'll give us a chance to do some integration on here. And here's what we have. The current in the long straight wire is shown is upward and is increasing steadily at a rate di dt. So switch back to my black pen, which is what I usually try to use. At any instant, or at an instant when the current is I, what are the magnitude and direction of the field B at a distance R to the right of the wire? Okay, well, we can use Ampere's law for this, that imagine yourself looking down the wire. And so here's a wire and the current's going into the page. And so it's got a current lowercase I. Point your thumb in the direction of that current and your fingers will point in the direction of the magnetic field. So the magnetic field here will be these concentric circles around this thing. And Ampere's law says that the integral around a closed loop of B dot, I think they use DL, but I can't remember. B dot DL is going to equal mu naught I. Okay, well, if we're stay a fixed distance away from the wire, B will be constant. It'll always point in the direction of DL if we integrate in the clockwise direction. And we can change the B dot DL into the integral around the loop of BDL because they're in the same direction all the time. B is constant, so I can pull it out and I get B times the integral around that circle of DL, and that's just going to be the circumference of the circle, which is B times 2 pi. How far away were we from the wire there? A distance R. Okay, so B times 2 pi R, and that'll equal mu naught I. And we get to this expression for the magnetic field of a long straight wire. It's B is equal to mu naught I over 2 pi R. Okay, now with the current going in that direction, point your thumb in that direction, the electric or the magnetic field to the right of that wire is going to be into the page. So instant current is I. What's the magnitude and direction? Well, we just figured out the magnitude. B is mu naught I over 2 pi R. And the direction is into the page. So we have that. Okay, what's the flux? D flux of B through the narrow shaded strip. Okay, well, the narrow shaded strip here has a width dr and it has a length L. And so its area is going to be that length times the width, or LDR. So this is for part B. And this will just be a dA in this case. It'll be LDR. And the flux through that, the flux of B will equal B times that dA, which is going to be mu naught I over 2 pi R. dA is LDR. So we have that. What next? Let's see. What is the total flux through the loop? Well, to get that, I'm going to have to integrate with R going from A over to B, I guess. And this is what I'll be integrating. So the total flux of B through that loop, this is part C, I guess. The flux of B will equal the integral over this square loop. And imagine that it's square. We've got pretty good curved corners on it, but I think that's just for a visual effect. At any rate, but we'll be integrating from R equals A to R equals B, from A to B of mu naught I over 2 pi R. What we're integrating is d phi sub B, so we just stick in our expression for that, times L times dr. And everything in here is a constant except dr and r. So I can yank that out and I'll get mu naught I L on top over 2 pi times the integral from a to b of dr over r. And I can do that one in my head. It's the natural log of r evaluated at a and b. And actually, a is on the bottom and b is on the top. It ends up being the natural log of b over a. Let me show you that. Um, Integral from a to b of dr over r will equal natural log of r evaluated at a and b, which is natural log of b minus natural log of a, which is natural log of b over a. So there we have it. Okay, so I guess the flux of B at any given time is just going to equal mu naught I. Was that supposed to be a lowercase I? Probably. Yes, it was. Mu naught I L over 2 pi and then the natural log of B over A. Okay, and then what's the induced EMF in the loop? Well, the induced EMF, this is part D, I guess. May run out of room soon, but that's all right. D is going to be induced EMF will equal minus d phi sub B dt. And the only thing that's changing in time in this expression is I. So everything else I can just stick out front. Mu naught L natural log of B over A divided by 2 pi times di dt. And I think they actually want a number for this. So we can plug in numbers for every one of these things, and we're given a value for d, what's lowercase I, di dt. Okay, anyway, we're given numbers for every one of these things. So let's go ahead and plug it in. Oh, no, that is the induced EMF in the loop. Okay, so part E is just to plug in the numbers and see what we get. So it will be minus, let's see, did we ever figure out the direction of the induced or the current in this thing? We have the magnetic field, magnetic flux into the page, di dt, it's actually increasing. So the magnetic flux into the page is increasing, which means the induced current will be in a direction to oppose that increase in flux and make its own flux in the opposite direction, which will happen if it goes in a counterclockwise direction. So out of there. But let's go ahead and plug in the numbers. Mu naught 4 pi times 10 to the minus 7th. Man, I've had the worst time with that one lately, remembering the units of it. And the one they give in the back is worthless. Webers per amp meter. Uh, let's see. I think a Weber is a Tesla per square meter. I can't remember. uh, Whoops, I'm in the wrong chapter for that. Oh, Tesla meters per amp. Okay. Oh, let's see. All I have on the bottom is 2 pi. Oh, that makes part of this simple. L was 24.0 centimeters, which is 0.240 meters. Okay, so far we'll have Tesla meters squared per amp. And then natural log of B over A, which is going to be B is 36 centimeters and A is 12 centimeters. So B over A is going to be 3.00 with no units. And then DI dt, 0.96 or 9.60 amps per second. Amps per second. And how does this look? The amps go away. Let's see, I'm going to have to remember that a Tesla is a Newton per amp meter. And let's see, that makes these meters go away. I already lost those amps. I'm going to have to think harder about this on a separate sheet of paper. Let's see. So Tesla meter squared times an amp per second. Oh, so that crosses out, that crosses out. Tesla meter squared per second. Supposedly, this is going to come out of volt. A Tesla is a Newton per amp meter times an amp per second. Oh, and I've got meters squared here. All right, that will go away. That divides out, I think. Oh, wait, I had already crossed out that one. Because a Newton, or yeah, Tesla meter per amp was what I had left over from this thing. I better back up a sec. Okay. Um, Tesla meter per amp on top. Oh, no, I hadn't. Times a meter, times an amp per second. Okay. So Tesla meter squared per second, but a Tesla is a Newton per amp meter. And I've got meter squared in a second. Okay, here we go. This will work better. On top, I've got a Newton meter, and on the bottom, I've got a amp second, but a Newton meter is a joule, and an amp times a second, an amp is a coulomb per second, so an amp second is a coulomb, joules per coulomb, or volts. Yay! All right. Well, that was a lot of work. Anyway, I think I lost track of my calculation, maybe. Of course. Okay, 4 pi over 2 pi is just 2. So I'll have 2 times 10 to the minus 7th. Times 0.24. Times natural log 3. Times 9.60. And I don't get much. I get an EMF of 5.06 times 10 to the minus 7th volts, which is not much. Okay, that's 0.506 microvolts. And so not a lot here, but this is only a single loop. If you want more, you have to wrap coils around. So that was a fairly complicated one there. The worst part, again, for me at least, was converting the units and convincing myself that I had volts. And that's how I make sure I haven't made a mistake, or one of the ways. So otherwise, the integral wasn't bad. Setting it up may be a challenge for you, and you may get some practice with that on the homework assignment that I'm going to post that yeah, do. Okay, now we've got something interesting. A long, thin solenoid has 900 turns per meter. That's not all that many, actually, and a radius of 2.50 centimeters. The current in the solenoid is increasing at a uniform rate of 60.0 amps per second, which is a lot, but actually, if you're doing that over a fairly short time, it doesn't mean that there's all that much current. What is the magnitude of the induced electric field at a point near the center of the solenoid, and A, 0.500 centimeters from the axis of the solenoid, and B, 1.00 centimeters from the axis of the solenoid? And both of these are going to be within the solenoid. So one thing I'll have to do is track down the expression for the magnetic field of a solenoid. And for this, I think I'm going to look at our spring quarter formulas for engineering physics, and magnetic field, long straight conductor on the axis of n circular loops, and somewhere here, aha, here it is. Magnetic field on the axis of a solenoid that has n turns per unit length. B is equal to mu naught n I. Things. And it turns out you don't have to be strictly on the axis. Inside is good enough. So we're going to imagine we're looking down the axis of the solenoid, and that magnetic field in there. And let's just suppose that we're looking at it at some instant like this. So looking like that. And B is equal to mu naught lowercase n times I. N is the number they gave us, and it is 900 turns per meter. So that would actually be 900. The turns is a dimensionless constant. It'd be 900 meters to the minus 1 is what it is. And the radius here is 2.50 times 10 to the minus 2 meters. I don't think we're going to have to do any calculations with the radius of it, actually, because we're staying inside. But here's the thing. I want to draw a great big circle. I'll just flip this piece of paper over to do it. So there's the center. And the reason I want to do this is this big circle is going to represent the solenoid, but we're going to be doing it at a couple of different locations inside this thing. And so there, I'm going to draw a couple of dashed lines. And I don't really care if I get the exact dimensions right on these dashed lines, but one of them like that, and another one, maybe I'll use that for another one, still within there. Yeah, I'll imagine using these two dashed lines. One of them's going to have the radius, the smaller radius of 0.500 centimeters. And the other one will have a radius of 1.00 centimeters, so twice as far out. And maybe I didn't do that bad on drawing these. except this is supposed to be 0.250 centimeters. So yeah, I did do kind of a crummy job, but that's all right. Um, that won't matter so much. Well, so that's what we need to imagine for this thing. And we want to know the magnitude of the induced electric field at a point there. Well, the induced electric field can come from the integral around a circle, and this will be E dot ds around a circle. And this is kind of something that's kind of weird about electric fields in a place like this, but what we get, the induced electric field, is actually a circular electric field, kind of like the magnetic fields that we've seen, except it's going in a full circle. We haven't had an electric field with a shape like that before, but that's what gets induced when you have a solenoid and the current through the solenoid changing in time. So that's what it would end up equaling, and this will equal the negative of d phi sub b dt, and well, an expression for the magnetic field strength in this case. Actually, this is going to be, it'll be the flux of B through the circle that we're integrating around. And so this expression here will just integrate in the direction of the electric field so that E and ds are pointing in the same direction everywhere, and this turns into E ds with no vectors. The E is constant, we can pull it outside, and so E will equal this E, that's EMF, this is electric field strength, and it'll be E times the integral around the circle of ds, but that's just going to be 2 pi r. So E times 2 pi r, and we're just after the electric field this time. This is going to be kind of weird. Well, the flux of B through this circle that we're tracing out by integrating around it, T, that'll equal the magnetic field strength times the area of the circle that we integrated around, which is just pi r squared. Okay, and the only thing changing in time is the, oh, and then the magnetic field strength is going to equal mu naught Ni. Forgot about that one. So I'll have the electric field times 2 pi r is going to equal minus d by dt of B, which is mu naught Ni times pi r squared. Okay, now constant, 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 a particular value for the radius, not changing in time. And so these things all come out, and the only thing left inside for the derivative is di dt. So I'll have mu naught n pi r squared with a minus sign, I guess, and di dt. And it says here we've got it increasing at a uniform rate. So magnetic field strength is increasing, but we're just after the magnitude of the induced electric field, so I don't care about the minus sign here. But here's something interesting. E is going to equal, solve for that, divide both sides by 2 times pi times r, and I'll have mu naught, and I'll just say the magnitude of E, mu naught n, let's see, pi r squared di dt. So I think I got everything on that side, divided by 2 pi r. Well, the pi's divide out. R squared over R is just R. And here's something interesting. Mu naught N times R times di dt over 2. Yeah, R squared over R just leaves me an R. But here's the thing. The electric field strength in here increases linearly. It'll be 0 at the center, and it increases linearly, steadily, as you move out toward the edge of the solenoid. Once you get outside the solenoid, actually, in this case, there is no magnetic field outside the solenoid because it's restricted to the interior of the solenoid. But that electric field increases linearly. So if we figure it out for 0.500 centimeters from the axis, for part B, all we have to do is just double the value that we get. So let's see what it is. Because that mu naught is 4 pi squared times 10 to the minus 7th, it's not going to be a whole lot, except that this is 900, so that'll help a little. And this is 60, but let's just see what happens. For part A, we'll be using R as 0.500 meters, and plug in the numbers. 4 pi times 10 to the minus 7th, and where did I do that last problem at? Tesla meters per amp. I don't know why. I just have a hard time remembering that one. That's mu naught. Okay, and times N, which is 900 times 1 over meters. I'll just leave it at that. R, in this case, is going to be half a centimeter is, that's 5.00 times 10 to the minus 3rd meters. So have that. di dt is 60.0 amps per second, which is 60.0 coulombs per second squared. Oh no, I'm going to write it as an amp per second because I've got an amp down there. And I think that's everything except for this 2 down here on the bottom. So unit-wise, what's going to happen? This meter will divide with this meter. This amp will divide with that amp, and I'll have, let's see, Tesla meters per second when I'm done. And I'll do some work on that, but just keep track of that. Tesla meters per second for the time being. And it probably comes out to a Newton per Coulomb is my guess. Okay. 4 pi. This becomes 2 pi times 10 to the minus 7th. Okay, and here's hoping that I plugged all this in right. I would get 1.70 times 10 to the minus 4th. And I'm expecting volts, but I'm going to evaluate a Tesla meter per second. Tesla meter per second. A Tesla is a Newton per amp meter. So that'll be a Newton per amp meter times a meter per second. Let's see. Meter. An amp times a second is a coulomb. A Newton per coulomb, that is our unit, or a volt per meter. Either one of those, they're identical, but that's our unit for electric field. So newtons per coulomb. Okay, and that's not all that strong an electric field, but still it's there. And if we double the distance, if we go to part B, we'd get twice that. So for part B, the value for the electric field would be 3.40 times 10 to the minus fourth newtons per coulomb. So fairly complex problem, but it's kind of neat that that's the direction of the thing. Now, I don't have time to do this next one. This is another solenoid. I may save this one, but we have a charge that moves in a circular path centered on the center of the solenoid. And the circular path is 3.50 centimeters in radius and lies in a plane perpendicular to the axis of the solenoid. Okay. If the charge moves around the circular path in the direction of the induced electric field, how much work is done on the charge during one complete trip around the path? Whoa, that's kind of interesting. And turns out there's a continual force on it as it's going around the path. That's not the way electric fields have behaved before. Before, if you started at some point and did a bunch of wiggling around and came back to the original point, the electric field would be no work. There'd be no work on you. But in this case, there is work and it just keeps going and going. And that's a non-conservative field. The electric field that's created by electromagnetic induction is a non-conservative field, which means if you do a complete path and came back to where you started from, the net work done is not zero. So that's kind of neat, but we'll have to save that one for another day because it takes a while, like 15 minutes. Anyway, that's a good batch of problems. This stuff is mind-boggling. So take the time to read this chapter and get a good grasp of it. The Lenz's law section, it may help to go through that one fairly slow and look at their examples and interpret the illustrations and things like that. It's a challenge. Okay, stop the recording.